be looking at the topic encoding theory. So, before we look at the code, let's first understand what coding theory means in mathematics. Coding theory is a branch of applied mathematics and computer science that focuses on detecting and correcting errors that occur during data transmission. Whenever we send data like messages, images, or files across communication channels, noise or interference can cause bits to flip from 0 to 1 or vice versa, which may cause an error, and this leads to data corruption. To avoid that, we use error detecting and error correcting codes. Coding theory helps us design mathematical techniques that add extra redundant bits called parity bits to the original data. These parity bits don't carry information themselves, but they allow the receiver to check and even correct any single bit errors that occur. One of the most famous methods used for this purpose is the Hamming code invented by Richard Hamming. It's a simple yet powerful example of how mathematics ensures data reliability and accuracy in digital communication systems. Now let's understand the Python code that demonstrates how the Hamming 7,4 code works. So first up, we have the import statements. At the start of the code, there are two import statements importing two modules, time, which is used to add small delays for smooth output, and the rich UI library, which allows colorful and formatted printing on the console, which is going to be a terminal for viewing the output. Then we create a console object using console is equal to console brackets. This object helps in printing messages and tables with colors, making the demonstration more visual and engaging. Moving on, we move on to the first function of the program. The first function is Hamming encode with the argument data bits. It takes a 4-bit binary input, for example, it could be 1011. Inside, these bits are converted into integers and arranged in a 7-bit structure that includes 3 parity bits. In Hamming, parity bits are placed at positions 1, 2, and 4, while the data bits occupy the other positions. So the arrangement might look like P1, P2, D1, P3, D2, D3, and D4. The parity bits are calculated using XOR operations where P1, P2, P3 checks bits at its own positions. These parity bits allow the receiver to detect and correct single bit errors. After encoding, the program prints encoding complete and displays the encoded code word in a rich table which clearly shows each bit position and its value in the output console. Moving on, we have error introduction and we have two arguments here, which is code and position, where it might happen during data transmission where an error might get introduced during the data transmission. It flips one bit at a specified position. For example, if the bit at position 4 is 1, it becomes 0. This is done using the XOR operation. Code of position -1 to the power is equal to 1. The output shows that an error has been introduced and the corrected code word is displayed in a table for clear visualization of the user. So this is the formula that we use here. Moving on, we have the function having decode, which performs error detection and correction. It recalculates the parity bits called syndrome bits, which we've mentioned this in a comment, to check if any bit is incorrect. The combined value of these syndromes gives us the error position. For example, if the syndromes form the binary number 0, 1, 1, that means the error is at bit position 3. If an error exists, the program corrects it by flipping that bit back. If no error is found, it prints the data error-free. Finally, it extracts and displays the original 4 data bits from the corrected code word, which we can see from here to here. And finally, we have the visualization function, which is display code table with two different arguments. This function displays the rich UI table format to show us each bit's position and value, making the whole process from encoding to error correction easy to visualize and understand with a better user interface for the user to view the output. Finally, we have the main function. In the main function, the program prints the heading coding theory demonstration and Hamming code 7, 0, and it takes the data bits 1, 0, 1, 1 as the input, and then it introduces an error at bit position 4 and then decodes and corrects it, showing entire process step by step. So now the coding part is over. We can move on and view the output. So now to view the output, we have run the code and we need to view in the terminal section. And as I've mentioned, we have the heading visualized perfectly, and we have the input of the original data bits, which is 1011. And from the encoding function, we can see the encoding has been completed, and the encoded Hamming code word is printed here with every bit position and its right bit value, meaning we have 1, 2, 3, 4 having 0, 1, 1, 0, and the next three positions having 0, 1, 1. Now, from the introducing the error function, we have introduced an error at bit position 4, and we have a corrupted code word at the position 4. As you can see over here, it's 0, but here the corrupted code word has 1. So we need to decode it. So moving on to the decoding and error detection part, we have detected the error is at bit position 4. So the error has been corrected successfully at bit position 4 from the decoding and error detection part, and the corrected code would has again been printed where 4 has 0 like in the initial stage. Moving on, we have the input being decoded data bits have been printed, and then the output decoded data bits have also been printed. To give more clarity, we can again go through the whole code where we have the encoding part where we have the calculation of parity bits over here, and then the output console print, and then we have the error detection function over here where we simulate an error at using this formula, and we have the decoding and correction part, which is the most important part, which corrects and decodes the final answer. Again, we have our calculation of syndrome bits, and then we find if there's an error position or not, and then we print accordingly. And then we have a visualization function which visualizes the entire table in a beautiful manner with colors, as you can see, for example, in this scenario. So with that, the coding theory is completed and we've successfully executed the program. Thank you.